we're going to talk a bit about curve sketching. So curve sketching uses the first derivative and the second derivative to be able to find a rough sketch of the graph. Now, what we'll do is we'll kind of like just run through a type of sketching. So let's say that we want to find the sketch of y equals to negative x cubed plus 3x plus 2. Now, for this equation, what we can do here uh, is look at, for example, um, the first derivative. But actually, let's go ahead and just say like what the domain of this function is. So we know that the domain is minus infinity to infinity. This equation has that it also has a range of minus infinity to infinity. Now, usually we don't tend to get too caught up on, for example, like x-intercepts and whatnot. Um, but most likely you can find the x-intercepts for this one because I can see, for example, that -1 is one of the x-intercepts. But really try not to get too caught up on, like what is the x-intercept. Okay, so the other thing that I notice is that the behavior of this polynomial is that it's negative and it's odd, meaning that it's going to be in this format where we have that it's kind of like in this diagonal motion where you have that it rises to the left, sorry, and it falls to the right. So let's actually look at the first derivative of this equation. So y prime is equal to negative 3x squared plus 3. Now what this means is that basically we have that if we factor out negative 3, we have x squared minus 1. From here, we basically have that this is going to tell us that there's a critical point at the two values x equals plus or minus 1. Now, this tells us that basically we have that we can figure out, for example, like what is the behavior of the graph if we use -1 and 1, and then we find some test points such as like 0, 2, and -2. But if we plug this back into our derivative function, we have that if we plug in 0, we'll get that this is going to be positive. If we plug in 2, well, 2 squared minus 1 is going to be positive, but times -3, that's going to be negative. So we have that this is going to be a relative max. And over here, if we plug in -2, it's the same thing really. So you have that's going to be negative, and this is going to be a relative min because you have that the function looks a bit like this, which is consistent with what we said about how the end behavior looks like that. So we go ahead and we take the second derivative. So we have that the second derivative is equal to -6x. But that tells you that -6x will give you an inflection point at x equals to 0. Now what that means is that basically you have that there's uh, a point where the concavity does change. So like if you choose -1, that's going to be positive, so that's going to be concave up. If that's 1, so that's going to be negative, so negative, so that's concave down. So in this case, we have that there is a change of inflection or concavity at 0, 2. So for this one, we have that changes at 0, comma 2. Okay, so this is going to be, okay, so we'll just put 0, comma 2 for this one. And back over here, we had the, we had the critical points. So when we plug in 1, well, that's going to give us 4, so 1, comma 4. But when we plug in negative 1, when we plug in negative 1, that's going to give us 0. So we have that this is going to give us, let's see, this is going to give us, yeah, 1, 0. So we called the 1, 4, um, we called it the maximum. And then we have that negative 1, 0 is a minimum. Oh, so this is going to be minimum. So the next step is that all that we need to do is plot all of the important points. So, okay, let's do that. So all that we need to do is just draw the x and y axis. So we have the xy axis as follows. Okay, now we have that there's going to be an x-intercept at negative 1, 0. Okay, so we got that one because that was the min. We also have that there's a y-intercept at 0, comma 2. So we have this point right here. But then we also have that there's another important point, of which this is 1, this is 2, this is 3, so then we'll say that 4 is right about here. So we'll put 4 right there, and we'll put 1 right there. Okay, so all that we need to do is connect the dots as they relate. So let's go ahead and draw our graph. So we know that the behavior of the graph is such that it comes down from over here. So we'll just draw it like so. Actually, it's the other way around, isn't it? Yeah. Okay, so okay, so we have that the graph. Let's do this again. So what do we have? We have negative 1, 0, and we have 1, comma 4, but then we have 0, comma 2. So this has to be concave up. So let's see. Okay, so if we go ahead and we say that this is decreasing to negative 1 and that's increasing, but you have that it's the minimum and it's also the x-intercept, then that means that the graph is actually going to bounce right off of negative 1. So we have something like this. Okay, so this is very rough sketch of our graph, but the logic is that if we plot more points, then in that case becomes a more accurate that becomes a more accurate sketch. So this is the x-axis and this is the y-axis. Now note that that's your relative min, and that right there is your relative max. Now interestingly enough, this point right here that passes through the x-axis, that's actually 2 comma 0. Um, Basically, what happened is that we have that the equation that correlates to this function is y equals negative x plus 1 squared multiplied by x minus 2. So this would have been the actual equation that you would use, and for this one it's more beneficial because now you can tell that there's an x-intercept at 2 and that there's an x-intercept at negative 1 and that there's a direct cross and then there's a bounce off of negative 1. So whenever you have it of this format, it's actually a lot better. But notice that you would have had to use a chain rule and also product rule in order to compute those first derivatives, second derivatives, and so on. But the algebra is a bit nicer in this sense if we use this format. So maybe you should try, for example, uh, using this format and see if you get the same thing. Now, let's say that you're looking at another type of equation. So let's say that you want to find the graph of y equals to 16 divided by x squared plus 4. Now, suppose that basically that you just want to find uh, using perhaps like the second derivative in this case. So we can say that like first we want to find y prime. So y prime using reciprocal rule is negative 16 times 2x divided by x squared plus 4 to the second power. Now this equals to negative 32x divided by x squared plus 4, and that's to the second power, which means that this gives us that we have a critical point at x equals to 0. Now I can either just stop here or continue. By stopping, I mean I can figure out like what are the intervals of increasing, decreasing. But let's say that we go ahead and we just find y double. Okay, so y double is equal to, now negative 32 is just a constant, so let's just leave it at that. So you have x squared plus 4 squared multiplied by 1 minus 2 times x squared plus 4 multiplied by 2x multiplied by x. Okay, that's a little strange, but we'll get there. And all of this is divided by x squared plus 4 to the fourth power. Now, what that means is that this is going to simplify a little bit. So we have negative 32 multiplied by x squared plus 4 multiplied by x squared plus 4 um, minus 4x squared. Okay, so we'll go ahead and simplify this in a bit. And this is all divided by x to the fourth, x squared plus 4 to the fourth power. Now, in this case, like if we go ahead and we simplify it even further, we'll notice that a factor cancels out. So that tells us that we have negative 32 multiplied by 4 minus 3x squared, all divided by x squared plus 4 to the third power. Now, this tells us that we basically have two inflection points because it tells us that you have that when you solve for this, you have that the inflection point is, let's see, it's going to be x equals to plus or minus uh, 2/3 root 3. So we have that that's going to be 2/3 root 3. Now, and the way that I found that was that I just said 4 minus 3x squared is equal to 0. So in this case, we can go ahead and say that, okay, yeah, that's what the inflection point is. Okay, so next is to basically just say that, well, if you were to, let's say, for example, figure out that this is negative 3, 2 root, negative 2 root 3 divided by 3, and then you have positive 2 root 3 divided by 3. So if I pick like 0, which is actually my critical point, if I pick, let's see, if we use our calculator, we can actually figure out that 2 divided by 3 multiplied by 3 raised to the 1/2 or the square root, that's 1.15. So we have to pick something bigger than that, so that's going to be maybe 2 and negative 2. Now note that basically this is going to do the same thing on this side. So if I plug in 0, I have that it's going to be negative. If I plug in 2, well, I have that it's actually going to be positive. But if I plug in negative 2, it's still the same thing. It's going to be positive. Now, the reason that it's positive is because if you were to plug in the 2, you would have 4 minus 3 times negative 2 squared. And this is all divided by negative 2 squared plus 4 to the third power. So notice that this is going to be 4 minus 12. So negative 32 times 4 minus 12. Well, definitely all of this is negative. And this is 4 plus 4, and that's cubed. So all of this is definitely positive. So what this tells me, though, back over here, is that at 0, so at 0 you get 4. So that means that 0 comma 4 is actually a maximum. So in that case, we already know that, yeah, 0 comma 4 is a maximum. We can actually plug in, for example, the remaining part of 2/3 root 3 as our inflection point into the equation. So like, for example, we have that y of 2/3 root 3 is equal to 16 divided by, okay, so that's going to be 4 over 9 times 3 plus 4. So in this case, what I can probably do here is say that that's going to be 4/3, so that equals to 16 divided by 4/3 plus 4. And then from here, I can probably just say that that's going to be 48 divided by, let's see, if you multiply this by 3, that's going to be 4, and that's going to be 12, which that's going to be a 3. Okay, so that's pretty crazy that that's going to give you a 3, which means that the other one is probably going to be, it's going to be a minus, oh, wait, you're squaring it, so it's going to be the same. Yeah, so it's going to be the same. So that means that y of negative 2/3 root 3, when you plug it back into this equation, 16 divided by negative 2/3 root 3 squared plus 4, that's also going to equal to positive 3. Okay, so that means that we have enough information. Now, keep in mind that the inflection point is like negative 1.15, so it's very close to 1. So that means that I have enough information, but I want to make one last note. The note is that if I take x to plus or minus infinity for 16 divided by x squared plus 4, this guy's bottom heavy, so in that case that means that it goes to 0. So that means that in actuality we have more that goes to this equation over here. This equation, or I'm sorry, this important point, it's actually an absolute max as well. So in that case, we know that that's the absolute max, and the absolute min does not exist, nor is there a min. So, okay, that's one thing to know. So we have that if we draw it, though, we can draw it just like we see it based on the information, because note that when we found that 0 was a maximum, then that means that we have to have that um, the function increases to 4, but then it decreases. So we have that there's an important point right here, and then you have another one. It's like at 1.15, so it's like right about mm, maybe maybe like right about here. Okay, so all that we need to do is to go ahead and just connect these. So we have that we just connect it. Okay, so it's a bit of a rough sketch because it looks a little flat as you get closer over here. I mean, we could do it again because it does look kind of funny. And maybe we'll just draw it without using the points, then we'll just label it as needed. So yeah, we have that the equation should look something like this. So here, we'll just have to put right here, like right about here. And right about here. That's where we're going to place 3. So we have that this right here is 3. And then this right here is the 2/3 root 3. Then this right here is the 2/3 root 3. So in this case, like this is what our approximate sketch of the graph will look like. Okay, so the next thing to do is to look at one more example. So when we look at one more example, we see that, let's say that we want to find the graph of y equals x plus 1 over x. Well, this is kind of interesting because basically if we were to rewrite it like x squared plus 1 divided by x, I already know that this goes to positive infinity. So this is gonna, and that's for positive infinity. As it goes to infinity, it goes to positive infinity. But as it goes to negative infinity, it's actually going to go to negative infinity in this case. Okay, so the way of which that will do this, okay, so I'm just going to put plus or minus infinity. The way in which that we're going to do this is that we're going to go ahead and just look at the first derivative. So the first derivative says that I have 1 minus 1 over x squared. So basically this tells me that if I set this equal to 0, I have 1 minus 1 over x squared equals to 0, which basically means that x squared equals to 1. But if we have that, basically this tells us that x equals to plus or minus 1. So these are our critical points. So we have that the critical points are right there. Now I can actually classify them though as I look at where it's undefined at 0 because you have that right here. 0 can't be. So you have that 1 and then you have -1. So if you plug in values between here, such as a half, maybe 2, maybe -1/2, and then maybe like -2. So if I plug in 2, well, that's going to be positive. So I have that that's going to be positive right here. But then I also have that if I plug in 1/2, well, that's actually going to be negative. So I have that that's going to be negative. Now what that means is that basically I have a min at 1, comma 2. Oh no, 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 not 1. 1 comma 1.5. Um, yeah, so if I go ahead and I plug in -1 though, basically that's going to give me -2. So we have that if we plug in -2, and I got the -2 just by choosing a test point. -2, that's going to be 1 minus 1/4. So yeah, that's going to be positive. So this is going to be positive as well. And then from here, if I plug in -1/2, it's basically going to give me the same thing. It's going to be negative. Okay, so interestingly enough, we have that it is undefined at 0, but it's also undefined along this asymptote right here. So try not to forget that this is a slant asymptote. Okay, so the next thing of which that we need to do is to graph our equation based on this. So earlier I was mentioning that, yeah, if I plug in 1, I get 1.5. If I plug in -1, I get -2. That's plugging it back into the original function. We forgot to find the second derivative. So finding the second derivative, you're going to find that y double equals to +2 over x cubed, which basically means that you only have that you just need to find what happens for less than 0 and for greater than 0. For greater than 0, you're going to find that it's positive, because if you plug in like 1, you get 2. But if you plug in -1, you get -2, so that means that it's negative. But what this means is that um, the graph of it looks where you have that it's concave down and concave up. So, okay, this is going to be a little interesting. So if we go back and let's say that we go ahead and now we can go ahead and just graph this equation because there's no inflection point. Okay, so we have that this is our x and y axis, and let's just draw the y axis. Now we have to draw an asymptote at y equals x. Okay, I think this is good enough. Now note that there really was no there really was no x-intercepts in this case. So we have x and we have y. Now we've already determined basically that there is only a minimum and there's a maximum. So if we go and we basically like plot, okay, so let's do this. Okay, so let's draw our graph, saying that we have something like this. And then we have our other part of the graph, which will be somewhere down over here. So we have that this is going to be like that. Okay, now what we'll do here is we'll just say that this point right here That's going to be the negative 1 comma, uh, let me see, negative 2. Yeah. And then this point right here, this is the negative 1, not 1, but 1 comma 1.5. Now to be specific, we have to classify this. So this is the min, but that's the relative min. And this right here is the relative uh, max. Now, if I would have probably, let's say for example, restricted the domain from 0 to infinity, this would be the absolute min, versus if I would have restricted the domain from negative infinity to 0, that would be the relative max and also the absolute max. Okay, so the main things that you would have to kind of know as it relates to graphing is, thinking of the domain, the range, the end behavior, um, and also if there's any asymptotes. Now, if you can find x-intercepts, that's great. If not, sure not to worry about them too much. And then y-intercepts as well. Now, the rest is really just finding the local extrema and then finding the concavity. And then the remaining is basically just plotting all points. By that I mean like, relative extremas and concavity and all that stuff. It should be note that in this previous example there was no inflection point. The rest is really just connecting all points with a smooth line. And then the last is that you can basically just verify with a calculator. Okay, so I think I forgot to include the increasing portions. So like for example, we know that this function, it increases from negative infinity to negative 1, union from 1 to infinity, and then it decreases from negative 1 to 0, union from 0 to 1. And then you have that the concavity, so it's concave down from negative infinity to 0, and then it's concave up from 0 to infinity. Basically, you would have to include the same thing for these questions right here. So here you have that there's an increase from negative infinity to 0, but that it decreases from 0 to infinity. You can mention the concave up, concave down. So like it's concave up from negative infinity to 2/3, negative 2/3 root 3, and then union 2/3 root 3 comma infinity. But then you also have that it's concave down from negative 2/3 root 3 comma 2/3 root 3. Okay, I know it's a little crazy or it's a little messy, but yeah, we got to include those. Um, I think like we did include it for this one because we figured out the concavity for this one. So like you have that this one was concave up from negative infinity to 0. And then this one was concave down from 0 to infinity. And then we only have that this is increasing from negative 1 to 1. And then you also have that it decreases from negative infinity to negative 1, union from 1 to infinity. And then that would be it. So when you're doing these, don't forget to find uh, the intervals of increasing, decreasing, and then also the intervals of concavity, and that should give you what you want. Okay, so I'm gonna go ahead and just give you an example that you can try on your own using all of these characteristics. Um, let's see. Okay, so be sure to look at be sure to look at this example. Okay, so try y equals x plus 2 multiplied by e to the negative x and see what you get. I can give you like a small hint. The x-intercept is negative 2 comma 0, and the y-intercept is 0 comma 2. Okay, so from here I'll just leave it to you on how do you find the sketch of this graph. Now don't forget that you do have a way of checking this using your calculator, but you can also check all graphs on desmos.com if you type them in, and then it just gives it to you right away.